Hello and welcome back, everybody. Today in calculus, we're going to be talking about positions, velocity, and acceleration. So these are all the things that you find normally in a physics textbook, but now we're going to look at it from a calculus perspective and how are those two things related to each other. So first of all, let's go ahead and start by saying the following then, or just to give you an example. Let's say that S of t is going to be a displacement equation in terms of meters, just again as example. And at time t, that is in terms of seconds. So we have a function of displacement in terms of time. And you have the meters and you have the seconds for the units. What I like to do is solve for the derivative and see how they're related to each other. Well, if you're solving for the derivative of s of t, we can first of all denote that as s prime of t, but I usually like to call it dt, d dt of s of t, because here you're specifically saying that you're taking derivative with respect to t, which is actually very specific, which is good. Again, later on when you start having to deal with functions that are going to be multivariables, you have to say specifically which variables you're taking the derivative with respect to. Now, in terms of the unit, remember the derivative is supposed to be the slope, the rate of change, right, of y divided by the rate of change of t. So if we're looking at units, then that means that this guy, what we're going to get is something that is going to be in terms of meters per second. And that in itself tells me that this is going to be velocity right here. So we can go ahead and say that that's equal to v of t then, because because we have meters per second. And to be a little bit more specific, you're solving for the instantaneous velocity at any given point. Now, go a little bit further. If I take the velocity equation, right, and take its derivative and think about its unit, then that means it's going to be meters per second squared. And thinking how that is related then to what we're dealing with, well, then that is going to be equal to the acceleration. So that is going to be our second derivative. So in conclusion, if my original equation is displacement, meaning positions, then the first derivative is going to be velocity, and your second derivative is going to be acceleration at any given time. Now, we can technically go further and solve for the derivative, but for the most part, that's just really fun because we don't really deal with the third derivative or the fourth derivative in the calculus portion of physics. But for those of you guys that are interested and just want to be entertained, the third derivative, that is going to be meters per second cube, and that is what is known as the jerk. You probably want to ask your physics teacher as to what that is. But you know what? For us, let's just go ahead and be satisfied with the idea that this is a jerk. And if you want, you can go ahead and start a trend where you can start calling your friend the third derivative if you want. And finally, just to go even further, if I solve for the fourth derivative, notice here we have the fourth derivative indicated by the fourth Roman numeral right there. That is what is known as the snap. But at that point, we're just kind of doing some fancy math that we don't really need. Okay, so as again, we are going to focus on just the position, velocity, and acceleration for our calculus portion of physics. So let's go ahead and begin then. Let's say that the displacement equation is defined by s of t is equal to t cubed minus 4.5 t squared minus 7t. I want to know when is the velocity equal to 5. So then that means, according to what we just said, I would like to solve for the velocity equation, which is going to be the derivative of our displacement equation. So that's easy enough. That's going to be 3t squared minus 9t and then minus 7. And then all that is going to be set equal to 5 because I want to know at what time is the velocity equal to 5. So clean up this equation a little bit. 3t squared minus 9t minus 12 is equal to 0. T squared minus 3t minus 4 is equal to 0. So t minus 4 multiplied by t plus 1 is equal to 0. And that means my t is going to be equal to 4. Technically, t is equal to 1 also, but we're not going to go ahead and consider negative time because, well, just to keep it simple. Well, there it is. That's going to be my time then. Now, let's go further and ask, what is the acceleration when the velocity is equal to 5? Is the particle speeding up or slowing down? So then that means I need to go ahead and look for the acceleration equation. So let's go ahead and do that then. So the acceleration, which is supposed to be the second derivative, well, we can go ahead and find that by taking our equation right here from part A and solving for its derivative. So that's going to be equal to 6t minus 9. And I want to find out what is the acceleration at that velocity's time. So that means that I'm solving for s prime of 4, because that was my solution in part A, or equal to a of 4, whatever you want to call it. So that is going to be 6 times 4 minus 9, which is equal to 24 minus 9. So the answer is equal to 15. Now, that's the easy part. The tough part is, I want to know, is the particle speeding up or slowing down? Well, let's go ahead and take those two and translate it. I saw for v of 4, right, when the velocity is equal to 4, that is supposed to be equal to 5 from what's given. And then in addition to that, the acceleration at time is equal to 4 is equal to 15, according to what I just saw for in part B. Since my velocity is positive, then that means I'm going to be increasing, right? So then that means that my graph is going to be going up. Now, my acceleration is positive also, then that means that's kind of like saying that it's increasing and increasing. So that means you're actually going to be speeding up in this case. So in terms of like concavity, right, the way you can think about it is that there are 3 ways you can increase. You can increase like this linearly, you can increase like this, or you can increase like this. Judging by what I have for my numerical values, since my velocity is going to be equal to something that's positive, and also my acceleration is something that's positive, then one would say that the conclusion is that your graph is going to be doing something like this around that point then. So the conclusion is, looking at this right here, you're basically going to have something that is going to be speeding up then. Okay, because you can see how the acceleration is getting bigger and the velocity is getting bigger, then that means the whole thing is going to be speeding up. Okay, let's dig about that. Let's dig around that idea for a little bit, just to make sure that all of this is actually clarified. Okay, so here we have a total of 4 scenarios that we want to consider. What happens to velocity and what happens to acceleration? And I want to know which scenario is it that you're speeding up versus which scenario is it that you are slowing down. Now, in the first case right here, we have velocity is greater than 0 and acceleration is greater than 0. So as we said graphically, that looks something like this, right? You're going to be increasing and then you're going to be speeding up. So in this case, that means that you are going to be speeding up in this scenario, because you notice that you're going to get going faster and faster. It's like saying that your slope is increasing and the rate of your slope is also increasing. So therefore, you're just going to be moving up really fast. In the second case over here, it's saying that your velocity is negative and then your acceleration is negative. So going by what we have in the first case right here, then your graph is probably going to be doing something like this then. It's just the opposite of the first graph. Still, you are speeding up, but you're speeding up going in the opposite direction, okay? Because you're going downward really, really, really fast, okay? Now, let's look at the other 2 cases. What if your velocity is speeding up, but then your acceleration is slowing down? So that graph is probably going to look something like the first one, but it's going to be increasing, but it's probably going to have a different concavity, much like this guy over here. So in that case, if I were to draw it out, right, I notice that my velocity, my instantaneous rate of change, is still positive because it's increasing, but a of t, which is the rate at which the slope is increasing, is kind of slowing down. So as a result, this right here, this is going to be the slowing down case then. Okay, so slowing down. And you can probably conclude then, in the second case over here, when v of t is going to be less than 0, so that means your velocity is going to be going down, so it's decreasing. Whereas your acceleration is pointing in the opposite direction, then that means that your graph is going to be doing something like this. So that is also the case of where you're slowing down, because the velocity and acceleration are opposite of each other. So the conclusion is that, hey, you got to look at what's happening with the velocity and also the acceleration. In the first 2 cases, you'll notice that when the velocity and the acceleration have the same sign, in this case, both positive or both negative, then that means you're speeding up. But whereas when your velocity and your acceleration are at opposite signs, then that means you're going to be slowing down then. So here, let me just kind of write that as a conclusion. Okay, when a of t and v of t have the same signs, okay, then you are speeding up. But whereas if your a of t and v of t have opposite signs, so meaning one is positive and the other one's negative, then you are going to be slowing down. Okay, slowing down. All right, so that is going to be kind of like our, I guess, like analytical part of this then. Okay, let's take a look at this one last problem, and then we'll go ahead and call it a day. Here, we're going to have the following then. A particle has an acceleration of a of t is equal to negative 4 divided by, should be t squared plus 2. So let me go ahead and change that a little bit. So got to make sure that my variables are actually matching, right? And then we have v of 1 is equal to 6, and x of e is equal to e squared plus 3. So that means that the velocity at t is equal to 1 is equal to 6. And whereas for the position, when time is equal to e, the position is going to be specifically at e squared plus 3. I want to find the total distance traveled from the time t is equal to 2 to t is equal to 5. So this is kind of like a working backwards type of problem, because I am given acceleration and I need to work backwards in order to figure out what is the velocity and also then what is going to be the displacement. So let's go ahead and start that up and see what we can get out of it. Now, a of t is equal to negative 4 divided by t squared and then plus 2. So the first question you need to ask yourself is, what is the velocity? Meaning, what is my function where when I take its derivative is going to give me a of t? Okay. Well, the easy part is the 2. If you have a 2 right here, then that means its quote-unquote antiderivative is going to be equal to 2t, because if you notice, if you take the derivative of 2t, you get 2 then. The hard part is the first one. What function has a derivative of negative 4 over t squared? Well, just to save you a little bit of time, you definitely can probably figure out that it's the power rule. But to be a little bit more specific, it's going to be 4 divided by t. So you have to kind of like work backwards in this case. One of the things I learned about math a long time ago is that if you know how to go forward, you need to also learn how to go backwards. And that's exactly what's happening over here. Now, the one part that's going to be a little bit tricky is that I'm going to put a plus c at the end of my velocity equation, because the c is a constant, and if you take the derivative of a constant, it's going to be equal to 0. So then that means that all of these, there are infinite number of antiderivative equations in this case because of that constant over there. So we need to figure out what that constant is. Well, that's where this v of 1 actually comes in handy, because if we know that when t is equal to 1, the velocity is equal to 6, I can plug that into the equation and solve that constant then. Okay. Anytime you take the quote unquote, again, antiderivative, there should always be a constant that you have to consider. Okay. So let's go ahead and plug it in. V of 1 is equal to 4 divided by 1 plus 2 times 1 plus c, and that is equal to 6 then. So 4 plus 2 plus c is equal to 6. So that means that c is going to be equal to 0. All right, so that's kind of nice. So that means now my v of t equation is going to be equal to 4 divided by t plus 2t. Now we're going to go ahead and repeat the procedure one more time, because I want to go from the velocity equation to the displacement equation so I can plug that in. So now I'm going to go ahead and solve for that displacement equation. What function has a derivative of 4 divided by t plus 2t? Well, again, doing the easy part first, a derivative that has 2t, the antiderivative then would be t squared. For the front part, what function has a derivative of 4 times 1 over t? And as soon as I say 1 over t, you should be thinking to yourself, the natural log. So then that means my answer is going to be 4 times the ln of t. Now, technically, the antiderivative is going to be ln of absolute value of t times 4, but we won't get into that just yet because that's going to be another time. And since t is always going to be greater than 0, then we don't have to worry about that scenario. But just keep in mind that, yeah, this is technically the antiderivative. We'll talk about it in the near future. Anyhow, just like before though, I need to add a constant to this one also. So we're going to go ahead and say plus c1 because again, anytime you take the antiderivative, there's a plus constant. Right here, just to give you an idea as to what I'm talking about, if I have y is equal to x squared plus 1, y is equal to x squared minus 5, y is equal to x squared plus pi or minus pi, all of them have a derivative of 2 prime. Of y prime is equal to 2x. So that's why you can see that the constant actually matters then. Well, the final thing I'm going to do is, not the final thing I'm going to do, but the next thing I'm going to do is plug in e is equal to t to solve for that c then. So x of e is equal to 4 times the ln of e plus e squared plus c1, and that is going to be equal to this guy over here, which is e squared plus 3. So cleaning up my math right here, ln of e is equal to 1. So 4 plus e squared plus c1 is equal to e squared plus 3. Cancel out the e squared from both sides, move the 4 over, so c1 is equal to negative 1. So that means now my equation of the displacement is finally 4 multiplied by the ln of t, and then plus t squared, and then minus 1. Whew, that was a lot of work. Finally, what I need to do is I need to find the total distance traveled from t is equal to 2 to t is equal to 5. So then that means I need to find out the change in distance between the two then. So my final answer should be x of 5 minus x of 2, because I'm going to plug in 5 and 2 into the equation to find out what their displacement is and what is its change in this case. So my final answer, let's see, that's going to be 4 multiplied by ln of 5, and then plus 5 squared, and then minus 1. And then we have minus for the other part, 4 multiplied by the ln of 2, and then we have plus 2 squared, and then minus 1. Let's see, kind of combining a math right here. Then we have 4 multiplied by ln of 5 minus ln of 2. And then we have plus 5 squared minus 2 squared. And then we have minus 1 and then plus 1. So the 1's can cancel out. We have 4 multiplied by ln of 5 over 2. And then we have also plus 25 minus 4, which is equal to 21. So that right there is going to be our change in distance. And we're going to go ahead and keep it like this without putting in the calculator because we want to be exact. All right, thank you so much for watching. And please like this if you actually